This video describes a solution using geometric algebra to a divided triangle problem that is, or the solution is presented more completely in a PDF that is linked in the video description. The problem comes from the channel Mind Your Decisions, which has a great variety of interesting problems. And what we will solve here is not the original problem, but an adaptation. The original problem gives specific values for A1, A2, and A3. We will treat a general case. The ideas that we will use in this video are first the relationship between the outer product of two vectors and the oriented area of the triangle that is formed by those vectors. Specifically here, A wedged with B is equal to twice the area of this triangle multiplied by the unit bivector for the plane that contains A and B. And similarly, B wedged with A is a rotation in the contrary direction, so B wedged with A would be the negative of 2 times A times I. A second idea that we will use is how to find the intersection of two lines that are parameterized as shown here. And I'll give you a few seconds just to read that. So the idea here is that the intersection point is simultaneously the vector A plus some specific scalar multiple of u, and is also the vector B plus some specific scalar multiple of v. So we set those two equal to each other, and if lambda u, this scalar multiple, or this scalar factor, is what we want to find, then we eliminate the other scalar factor by taking the outer product of both sides with v. And when we follow through on that, we end up with lambda u times the outer product of u and v is equal to b minus a, its outer product with v. And then, of course, to find lambda u, we multiply both sides by the multiplicative inverse of u wedge v. So our solution strategy will be to express each of these three given areas, A1, A2, and A3, in terms of outer products of vectors, and then we'll also express the area of the full triangle in terms of outer products of two vectors. Then we'll find A4 as total minus these. So the GA formulation that we'll use here is shown with these three vectors, u, v, and w. In order to find the area of the full triangle, we will use the outer product of v with c. Now, how will we find the vector c? Well, we will use the intersection idea that we saw a moment ago. We can see that c here is just some scalar multiple of u. So we set vector c, which is lambda u, equal to v plus some scalar multiple of w minus v. Here we have done that. And what interests us is the scalar lambda u, so we will eliminate lambda wv by taking the outer product of both sides with w minus v. Thus we find lambda u as, well, you can read this here, and we end up with this equation. Lambda u times this outer product minus lambda u times this outer product is v wedged with w. Now from the original diagram, we can see that the outer product of u and v is, well, you can read it here, and v with w is this, but we don't yet have an expression for u wedged with w. So how can we get that? Well, I'll let you read this for a few seconds. we know that W is h3 over h2 times vector z. And because the triangle ABF and ABE have the same base, which is AB, then h3 over h2 is a3 plus a2 over a2 itself. And in addition, z wedged with u is 2 times a1 times I. So if we work through this, we end up with u wedged with w, that's in the opposite direction here, so it's negative 2 times a2 plus a3 over a2 times a1. So now we have a value for u wedged with w, and following through on that, this is where we left off last time, so we take up here. We have now that u wedged with w is this. So if we work all this out here, do some algebra, we end up with this expression for lambda u. Now that we have lambda u, we can find the vector c, which is just lambda u times u. Now finishing up here, v wedged with c, which is twice the, or v wedged with c is half the area of this triangle multiplied by I, is this. And if we work through all this and do some algebra, we end up with this expression for the sum. 2 times the sum times I is this. So now we just solve for a4, and that's the end of it. So a PDF of the solution again is linked in the description. I hope that you'll take a look at that. And I hope that you'll also consider joining the LinkedIn group that's the home of, well, the home group on LinkedIn for this YouTube channel. And I will also put that, or the link to that LinkedIn group in the video description. Thank you for your time, and I look forward to your comments.